Welcome back to yet another video on our channel Euclid Mathematics. We have started lecture series on CSIR NET SET Gate and other competitive exam. From few days I am solving previous year questions from complex analysis, linear algebra and all the subject which is important to CSIR NET SET Gate. So in my today's video I'm gonna explain to you all one of the solved question from previous year's CSIR NET exam. So which is completely based on a singularity chapter. Okay, so thereafter we have the division of a singularity into non-essential singularity and essential singularity. So let's get start our today's lecture. First of all, I'm going to explain to you all question, and then we'll move on the detailed understanding of our solution. So here in our question we have given consider the function. We have given in our question consider the function f of z which is equal to sine pi z by 2 upon sine pi z. Then f has a pole. Okay, so we have to check when we have pole for our function f of z. So before moving further, we need to understand first of all pole, removable singularity, isolated essential singularity, non-isolated essential singularity. Okay, now first of all, pole, when we put any denominator or any value it is 0, then it gives us a pole. Removable singularity says that if we have function 0 by 0 form and then after of it gives a finite or some exist value, then there exists a removable singularity. Non-isolated and isolated essential singularity, it says that we cannot define this function. Okay, now first of all we have to check whether our function is having pole or not. Okay, and in our first option we have given for all integer our f of z gives us a pole. Okay, for f of z gives us a pole. So we have to check whether it is a pole, having pole, whether it is having removable singularity or non-isolated essential singularity. Okay, so we have to divide that singularity from our question. So if our function possesses a removable singularity or non-isolated essential singularity, then we can say that our function do not have only the pole. But in our question we have given for every value, for all value our function gives a pole. Okay, now first option it says that for all integer. For all integer means for all values of a z, like a 0, plus 1, minus 1, plus 2, minus 2, plus 3, minus 3 and so on. For all these values of integer, our f of z sin pi z upon 2 complete divided by sin pi z gives us a pole. Okay, and we know that when we take sin n pi, okay, sin n pi, we get the function as a 0. Sin n pi is a 0. Okay, so it is easier to choose the integer. We have to choose here counter example to prove our all integer first option wrong. Okay, so we know that sin n pi is a 0, so try to take the even number. So if you consider n as a 4, okay, n which is equal to 4. If I consider n which is equal to 4 in our f of z, then our f of z, whether it shows pole or removable singularity or non-isolated essential singularity. So we have to divide this singularity here. Okay, so if it possesses other singularity than pole, then we may say that our first option is wrong. Okay, and how we check our function possesses pole or removable singularity or non-isolated essential singularity? For pole we show for a pole by using our function limit as a z tends to z naught. Z naught is a pole here, z minus z naught into f of z. Okay, so z naught is a pole. So to show our function exists pole or not, we use this result to show whether it is pole or not. So to show directly our function possesses pole, it is obvious case. Some values for integer maybe gives us the value that can our function can use the pole. But what can we do other than this? So if I show our function it possesses removable singularity, then it is easier to show our function example is a first option is a wrong. Now for removable singularity, we by using our function we have to show whether our first option is true or not. For that we show our function f of z possesses removable singularity for all even integer. Okay, so as I consider n which is equal to 4, take n which is equal to 4 and show that our function possesses removable singularity. And for the removable singularity we show that limit as z tends to z naught f of z. Okay, z tends to z naught f of z exists and gives finite value. Okay, it exists and gives finite value. Now limit z tends to z naught. Z naught I consider n which is equal to 4 as z naught as a 4. Okay, we have to check whether z naught which is equal to 4 gives pole or removable singularity or non-isolated essential singularity or any other. Okay, so limit z tends to z naught. So I consider here limit as z tends to z naught means z tends to 4, z minus f of z. So what we have f of z, which is a sine pi z by 2 upon sine pi z. Okay, so this is the f of z we have here in our question, and we have to put z tends to z naught. That means for 4 we have to show z naught which is equal to 4 whether it is a removable singularity, pole or any other singularity. If I put z naught which is equal to 4 in our question and it shows that it is not a removable singularity, that means it goes to some other possible chances. Might be it is a pole or might be it is a non-essential. So put z tends to 4 here in our sine pi z upon 2. So what we have, sine pi into 4. That means sine 4 pi divided by 2 upon sine 4 pi. Okay, and we know that sine n pi is always 0, so 0 by 2 upon 0, so it gives 0 by 0 form. It gives 0 by 0 form. If removable singularity gives us 0 by 0 form for some particular point, then what we do when we have limit as a 0 by 0 form, we always use L'Hospital rule. And L'Hospital rule, it says that we have to differentiate numerator as well as we have to differentiate denominator. Okay, so differentiate numerator here, sine pi z by 2. Okay, we have to take differentiation. It is not like a u by v rule. We have to directly differentiate numerator and we have to directly differentiate denominator. So limit as z tends to 4, limit as z tends to 4, sine pi z by 2. That means sine x, differentiation of a sine x is a cos x. That means cos pi z by 2 into differentiation of a pi z by 2, which comes 1 by 2 constant out here. Differentiation of a pi z with respect to z is the pi. Okay, and total divided by sine pi z. Differentiation of a sine pi z is a cos pi z. Okay, so cos pi z. So here I got the differentiation of a cos pi z into pi. Okay, now apply as a z tends to 4 here now. Okay, so we'll get the cos 4 pi by 2. 4 pi by 2 means cos 2 pi. That means cos 2 pi multiplied by 1 half pi upon apply cos 4 pi into pi, pi cos 4 pi. Okay, this is just substitution of a limit. Okay, so cos 2 pi into 1 by 2 pi. So when we apply 2 pi on cos, what is the value for cos 2 pi? We get the value 1. Okay, cos 2 pi is a 1, cos 4 pi is 1. That means cos n pi, when n is a even, then we get the value 1, and when n is odd, we get the value -1. So cos 2 pi is 1, cos 4 pi 1, so pi get cancelled, so we got the value 1 by 2. Now here we can see our function, first it gives a 0 by 0 form, but after applying infinite L'Hospital rule, it gives a finite value and exists. So our function exists removable singularity. Okay, so might be it exists for some other value. We don't have to care for this because we have to show our first option. It shows that for all integer our function gives pole, but when I consider n is a 4 as z naught is a 4, I got the removable singularity, which is a value 1 by 2. So our first function is wrong here. Okay, now here we can see our first function. I already solved here first option. Okay, so here we got the 1 by 2, which is a non-zero value and exists. Okay, so 0 by 0 form, and then z is equal to 4 has a removable singularity. Okay, if all even integer f of z gives us, so if z is equal to 4 is a removable singularity, so if you put z is equal to 8, always you will get the removable singularity. So for all even integer, f of z has a removable singularity, okay, but not a pole. If it is a removable singularity, then there does not exist pole. Okay, so f of z has a removable singularity but not a pole. Okay, so now here we can see for all, next option it says that for all even integer, it says that f has a pole, but we got the for even integer n is equal to z is equal to 4, it is even integer, I got the removable singularity. So for all even integer it is not possible. Okay, so option number B is also wrong here. So if we solve option A carefully while looking option B, so we can delete other option by using first option. Okay, now here option B is wrong here, so B eliminated. Now, so if you wanted to check with some counter example, you may go like this. Okay, so it shows that our option number B is wrong here. Now our option number C and D, it says that whether it is gives us a pole for odd integer or not. Okay, now let's check for odd integer to our function f of z. Okay, apply the definition of a pole over here, because we are not going to check now removable singularity. We checked it for even integer. Now we have to check for odd integer. So for that, take the definition from pole and find out whether for odd integer our function gives pole or not. Okay, so here is the solution. So here we have question f of z is equal to sine pi z upon 2 upon sine pi z. Okay, so when we get the pole, when we put their denominator of our function which is a 0, then we get the pole. Okay, so sine pi z, if I substitute sine pi z which is equal to 0. Okay, if I substitute sine pi z which is equal to 0, then I will get the pole from our function. So sine pi z is equal to 0, that means sine theta which is equal to 0, then we write theta is equal to n pi, that means pi z which is equal to n pi. Okay, pi z which is equal to n pi, so pi get cancelled, so it gives z which is equal to all values of a n, we get the pole here. Now let's check for which values and what order of our pole exists here. So for finding the pole, we use limit z tends to z naught, z minus z naught f of z. Okay, now for z naught we have here n. Okay, now select the z naught as n and let's check whether it is pole or not. So we have to check for odd integer. Okay, now n from integer here. Okay, odd integer, now select any odd integer. So it is better to select smallest odd integer, so it is easier to get these calculations. Okay, so if I consider z naught as a 3, okay, I consider z naught as a 3 and put it in our definition of a pole, it says that limit z tends to z naught means 3 z minus z naught into f of z. So what we have the value for f of z? Sine pi z by 2 upon sine pi z, which is a sine pi z by 2 upon sine pi z. So this is the value for f of z. So limit z tends to z naught, z minus z naught, sine pi z by 2 upon sine pi z. So if we are going to substitute z as a 3, so sine 3 pi by 2 and sine 3 pi. Okay, so it also gives us value 0 by 0 form. Okay, so if it goes to 0, so z tends to 3, 0 into the 7, it goes to 0 and 0 by 0 form. So our function, it gives us 0 by 0 form when we apply limit z tends to 3. Okay, so for that use a Hospital rule that can give us a value finite or infinite. If value does not exist here, then we say that it do not have pole for odd integer. Okay, we are checking for odd integer, and if value gives us a finite value or exist here, then we say that for odd integer our function gives us a pole. Here we can see I taken here z is equal to n as a pole and n belongs to z. You may take any element from n. Okay, so if z naught which is equal to 3, I consider here z naught is equal to 3 because we have to check it is for odd integer. Okay, so for odd integer whether it is having pole or not. Okay, so z naught is equal to 3. Now z limit z tends to z naught, z minus z naught sine pi z by 2 sine pi z. So when we put z is equal to 3, we get the 0 by 0 form. Apply Hospital rule. So you have to differentiate numerator as well as denominator. So sine pi z differentiation, cos pi z into differentiation of pi z by 2, which is a pi. Okay, so we have to differentiate further it. So now apply for the numerator here u into v, because we have two function. So then keep first function as it is, differentiate second, plus keep second function as it is, differentiate first. Okay, so we will get the numerator here. Now I put directly z tends to 3, so first term it goes to 0, so sine 3 pi by 2. Okay, and sine 3 pi by 2, what is the value for sine 3 pi by 2, which gives us a -1 value. Okay, sine pi by 2 1 and sine 3 pi by 2 -1, so sine 3 pi by 2 is -1, so pi cos pi z. Okay, and put value for z is a 3, so cos 3 pi. Okay, cos 3 pi it gives a -1 value. Okay, so when n is odd, cos n pi gives negative value, and when n is even, cos n pi gives positive value. So cos 3 pi is a -1 into pi, so negative pi, so -1 by pi, negative pi. So we got the 1 by pi as a value for our function. It is the pole of our function. Okay, so z naught is equal to 3 is a simple pole. Simple pole means here it is the order for that pole, it shows that function z minus z naught. So here it is the value for n, which gives us the order of our pole. So if we have n is equal to 1, then we write is the pole of order simple. Okay, so z naught is a simple pole of odd integer for value n. Okay, so it gives odd integer, for every odd integer it gives us a pole. So if we consider n is equal to 1, okay, so z naught is a 1, z naught is a 3, z naught is a 5, z naught is a 7, it always gives us a pole. Okay, so for all odd integer our function option number D is a true. Okay, for all odd integer our function gives us a pole. Now our next option number C here, for all integer of the form 4k plus 1. Okay, so 4k plus 1 and k belongs to z. So if I substitute k, the value for k, which is the 0, 1, 2, 3, we'll get the odd values. Okay, so substitute the value for our understanding, 4k plus 1. Okay, so if a k is 0 from integer, we get the 1. If a k is a 1 from integer, we get the 5. K is a 2, we get the 9. So we can see we got the odd integer here. Okay, so all are the odd integer. So for all the odd integer we got the pole, that means this value which belongs to odd integer. So for this value also we got the pole. Okay, so in our question, option number A, which is wrong, option number B, which is wrong. For even integer it is not always gives us a pole. Okay, but for odd integer we always get the pole for our function. So option number C and option number D, which is correct here. Okay, so that's it for my today's lecture. So I wanted to explain to you all here the question from CSIR NET, which is completely based on singularity chapter. So if you wanted to see more videos on singularity chapter, you may check it into my playlist. I already uploaded plenty of the videos there. Okay, so thank you everyone. Thank you for my today's lecture.